Hi everyone, in this video you will learn about band pass filter and band reject filter. So let's start with band pass filter. So in the last couple of videos, you've seen how to design a passive low pass or high pass filter. When you want to design a low pass filter or a high pass filter, what you need is an RC or RL circuit. So you can design low pass or high pass filter with passive components such as resistor, capacitor, or inductor. We saw that the low pass filter passes low frequency component from the input signal, while the high pass filter passes the high frequency component from the input signal. But sometimes in some application we are only interested in particular band of frequency. So what we are looking for is a filter with this characteristic. So we don't want to pass low frequency and we don't want to pass higher frequency. We are looking for a specific range of frequency, and let's say this range is something from omega C1, which is our lower cutoff frequency, to omega C2, which is our higher cutoff frequency. So this is what you can see here is an ideal band pass filter, and now we want to see how we can make a filter that behave like this picture here. So the band pass filter passes only certain band of frequency and rejects all other frequencies. Now there are many ways that we can design this band pass filter, and one of them is using a series RLC circuit. So in order to have a band pass filter, we can use a series RLC circuit In an RLC circuit, if you choose to look at the resistor's voltage as your output, so the voltage of resistor which is here, then the response of this circuit would be very similar to the output of a band pass filter. Let's see how it works. In order to analyze the response of this circuit, I would like to think about low frequencies and high frequencies and then medium frequencies. Let's focus on low frequencies. So if we are thinking about low frequency, what happens is that the impedance of Ls would be very small because S, or which represent our frequency, or j omega, is approaching to 0. So L multiplied something which is approaching to 0 is very small. So I'm going to draw my circuit in this form. So I have my input source connected to an impedance which represent Ls, and that's a very small impedance. Then I have 1 over Cs. Now let's assume that S is approaching to 0. 1 over a number which is approaching to 0 is a huge value. So I can describe this impedance in this form. So this is basically my capacitor impedance, which is 1 over Cs. I'm trying to show you, visualize that the impedance is getting bigger for the capacitor when we are thinking about low frequencies, and the impedance of inductor is approaching to 0 in lower frequency. And the resistor is just a constant number and it's not a very big number. So compared to the impedance of capacitor, that's a small impedance. Now, I'm looking at the voltage of resistor. So as you can see, the impedance of capacitor among these three impedances is the biggest one, and it's very far from the values of R and LS. So what happens is that if you think about a voltage divider between inductor, capacitor, and resistor, the biggest portion will be the portion for the capacitor. So the capacitor gets most of the input voltage, or VI, and a very small portion reaches to the resistor. So we can say, because the impedance of the capacitor is approaching to infinity, most of this voltage will be the portion for the capacitor, and a very negligible value of the input voltage reaches to the resistor. So VO in this scenario will approach to 0, because the impedance of resistor compared to capacitor is very small. Okay, now let's go to higher frequencies. Now, in higher frequency, this time what we have is a very big impedance for LS, because we're assuming that frequency is approaching to infinity. So L multiplied by infinity is a huge number. And on the other hand, 1 over CS is almost 0. And then we have resistor, which is a constant number, and compared to LS, that's going to be a very small value. So again, if I'm looking at the voltage of resistor, this time the biggest portion of input voltage reaches to the inductor, and the resistor have the minimum part from the minimum portion of input source. So again, we can assume that VO is approaching to 0, because comparing the impedance of resistor and inductor, the resistor is almost negligible, so its voltage is going to be very small as well. Now, let's see what happens in medium frequencies. In medium frequency, what will happen is that the inductor and capacitor, they don't have a big number. There are some ordinary values. So what we have is VI connected to the inductor, capacitor, and then resistor. So here we have LS, and here we have 1 over CS. We have inductor and capacitor beside each other. You know that whenever you add the impedance of these two, they cancel out the effect of each other. So if their value are close to each other, they can cancel out each other's effect. For example, if you have an inductor equal to J2 and your capacitor is minus J2, then they completely cancel out the effect of each other. So if you have an inductor and capacitor in series and they have same value, same amplitude for their impedance, which then what will happen is that they will cancel out the effect of each other. And then all your voltage, all your input voltage will reach to your resistor. So in this scenario, your VO is very close to your input voltage. So remember that if your inductor capacitor has an impedance which is approaching to infinity, then the other one will not be able to cancel out the effect of its neighboring component. So if you have an inductor which is infinity and a capacitor which is very small, then the capacitor cannot cancel out the effect of inductor, and what will happen is that all the input voltage will drop across the inductor, and same thing for the low frequency. So in low frequency, all the voltage will drop across the capacitor, and the resistor won't have a big portion of the input voltage. But when we are talking about medium frequency, in medium frequency, the inductor and capacitor, they have similar in the same range impedance. So what will happen is that they can cancel out a main portion of each other's impedance. So the most of input voltage will drop across the resistor. That's why if you draw the frequency response of this circuit, considering the output of your resistor as your output voltage, then what will happen is that you're going to see something like this. So in low frequency, the magnitude is 0, and in higher frequency, it will reach to 0 as well. But then somewhere in the middle range, you're going to have an amplitude for your h of j omega, which is equal to 1. So your VO over VI is equal to 1. And this frequency is your center frequency. Okay, so in center frequency, we have an ideal situation that the input voltage will be completely dropped across the output element. So our output voltage will be exactly equal to the input voltage. That's where the resonance happens. But the question is that what is basically the range that I can consider my output to be what is the range that I consider that my output is going through filter, and what is the range that I consider as reject band or stop band of my filter? So now let's take a look at frequency response characteristic. So in this frequency response plot, we are going to consider two frequencies to be our cutoff frequency. So the first one is going to be my omega C1, and the next one is going to be omega C2. And my cutoff frequency basically tells me which part of frequency will be considered as passed through the filter and which part will be considered as stopped by the filter. So if the frequency is between omega C1 and omega C2, then I'll consider them being able to pass through the circuit, and otherwise they will be stopped by the circuit. So this particular range from omega C1 and omega C2 is called my bandwidth, which I'm going to show it by beta. And I'm going to write it here. So beta is going to be equal to omega C2, my higher cutoff frequency, minus omega C1, which is my lower cutoff frequency. And the question is that where I can consider to be my cutoff frequencies. So the characteristic of cutoff frequency is that the magnitude of h at j omega, so your magnitude should be at least 1 over radical 2 of your maximum magnitude. Here the maximum magnitude is 1, so the cutoff frequency happens where h of j omega has a magnitude equal to 1 over radical 2. So in order to calculate my cutoff frequency, what I need to have is my transfer function, that I'm going to show you the transfer function of bandpass filter in next slide. So another component that I want to talk about here is the quality factor. The quality factor is described as omega naught, or my center frequency, divided by bandwidth. So if I know what is my bandwidth and what is my omega naught or center frequency, let me write this here. Omega naught is my center frequency, where I have the maximum magnitude for h at j omega. So if I have my omega naught and if I have my bandwidth, then I can describe my quality factor by dividing omega naught by beta. And the last equation that would be helpful whenever you're working with a bandpass filter is the relationship between cutoff frequencies and omega naught. I'm not going to show you the proof, but you can use this in your design and calculation. So if your center frequency is equal to radical omega C1 multiplied by omega C2. So this is always true as well. So these are three different equations that you can use in order to find different parameters of a bandpass filter. What are these parameters? So a bandpass filter has 5 parameters. Omega C1, this is the first one, omega C2, beta, and cutoff frequency, and then quality factor. So you can see that we have 3 different equations. So if you know 2 of these parameters, for example, let's assume that you know about the lower and higher cutoff frequency, then you can find the rest of them. So you can find beta by subtracting them, you can find omega naught, your center of frequency, by this equation, and finally you can find your quality factor. So every bandpass frequency has 5 parameters, and knowing 2 of them is enough to figure out the other 3 parameters. Okay, now let's take a look at the transfer function of the series RLC circuit, which has the output as the voltage of the resistor. Okay, so I'm gonna draw the circuit one more time here. So I have LS here, 1 over CS here, and R, which describes the output voltage. Okay, so in order to describe the transfer function, which is H of S, and describe VO over VI, what I need to do is using a voltage divider. So I want to see what is the voltage of resistor. So it's gonna be R over R plus LS plus 1 over CS. I don't like my transfer function in this form. I want to show it in a standard form, which I have a polynomial in denominator instead of this fraction. So I'm going to multiply everything by S first. So if I multiply everything by S, then this S from denominator will cancel out, and I need to make this one as S squared and add S here, and same thing in numerator. And then I want to get rid of the coefficient of S squared in denominator. So I'm going to divide everything by L. Now I'm going to rewrite my transfer function here. So H of S, if I rearrange and do the division, will be something like this. R over L multiplied by S, and then S squared plus R over L multiplied by S, plus 1 over LC. So this is the transfer function that describes a bandpass filter. Now you can check that by looking at this transfer function in low and high frequency. So in low frequency, I can say that S is approaching to 0. So then in numerator, I have 0. In denominator, this term will disappear. This term will disappear because they're 0. And I have a constant in denominator. So I have 0 over a constant. So it shows you that your H, the magnitude of H, approaches to 0. Now in higher frequency, if I look at my transfer function again, what will happen this time is that S is approaching to infinity. So in denominator, if S is approaching to infinity, I can neglect comparing s and s squared, I can neglect s and obviously the constant. So I'm just going to keep the highest degree in denominator. Now, if you have s over s squared, because the degree of your denominator is greater, then it's going to be your magnitude of h will approach to 0 again, and that's what we expect. So in a bandpass filter, we don't want to pass low and higher frequency component. We're only interested in middle frequency. So from the transfer function, you can also see that this transfer function is not capable of passing very low and very high frequencies. Something else that is very important here is that you can get two parameters from your transfer function, and then having those two parameters, you can go back to these three equations and calculate the other three parameters. Now, the question is that which parameter I can get from my transfer function. So the first one is omega naught. Omega naught is very easy to be calculated. Why? Because omega naught is the frequency in which the maximum happens, and your maximum here is equal to 1. So if you let this transfer function to be equal to 1, you can find the frequency that makes that happen, and that frequency is basically your omega naught. So if I want to solve this equation, I'm going to have r over L multiplied by j omega equal to j omega squared plus r over L j omega plus 1 over LC. Obviously, I have these terms on both sides of my equation, so they cancel out each other, and I'm going to have what will remain here is going to be 0 equal to minus omega squared. This minus is the effect of j squared plus 1 over LC. So you can see that your omega naught is equal to radical 1 over LC, or in another word, omega naught squared is basically equal to 1 over LC. Now, I just showed you what is your omega naught, but from now on, you can find it from the transfer function directly. So your omega naught is basically the constant that you have in denominator. Your omega naught squared. So remember that if you make sure that your transfer function is in its standard form, then you can use its constant in denominator as omega naught squared. What does it mean to have it in standard form? It means that you need to have a polynomial, a second order polynomial in denominator, in which the coefficient of s is equal to 1. So in that case, you can say that your constant is equal to omega naught squared. And something else that I'm not going to show you the proof is beta. So if you have everything in a standard form, you can use the coefficient of s as your beta. So the coefficient of s in denominator is basically your beta. And what you have in numerator is k multiplied by beta. So let me draw the standard form, standard transfer function of band pass filter. This is something very important to remember. The standard form for a band pass filter is k multiplied by beta multiplied by s divided by s squared plus beta s plus omega naught squared. So as soon as you have a transfer function in this form, you can say that this is a band pass filter, and the constant in this standard form represent omega naught squared, and the coefficient of s in denominator is your beta, and then what you have as the coefficient of s in numerator is k multiplied by beta. Now, because from this standard form you can find your beta and omega naught, then from the other equation that I showed you previously, you can find your cutoff frequencies and your quality factor. Let's do a quick example here. Let's assume that I have a filter, and I know that the transfer function of this filter is equal to 1000 s divided by 2s squared plus 1000 s plus 8 multiplied by 10 to 6. The question is that what is the filter type and what are the parameters of the filter? Okay, so because I'm looking at a second order transfer, a transfer function with a second order polynomial in denominator, I know that this should be a band pass or band reject. You don't know about the transfer function of a band reject yet, but for transfer function of a band pass filter, we know that we need to have s in numerator. So from the denominator that is a second order denominator, I know that this is either a band pass filter or a band reject filter. You don't know about band reject, and then later you can compare it, but for a band pass filter, I need to have s in numerator. So because I have s in numerator, then I can consider this as a band pass filter, not a band reject filter. Okay, so this is a band pass filter. Now the question is that what are the parameters of this filter? Is this transfer function in its standard form? No, it's not, because the coefficient of s squared is equal to 2 and it's not equal to 1. So I'm going to divide everything by 2 to get rid of the coefficient of s squared, and then I can consider my transfer function as a standard transfer function. So if I divide everything by 2, then h of s will be 500s divided by s squared plus 500s plus 4 multiplied by 10 to 6. Now here I can say that because now I have everything in the standard form, I can say the constant in denominator represent my omega naught squared, and the coefficient of s in denominator represent beta, and the coefficient I have in the numerator for s is k beta. So let me write the values that I have. So I know that I'm going to write it in another slide. Okay, so I can say that omega naught squared is equal to 4 multiplied by 10 to 6. So it means that omega naught is equal to 2000. So that's the first parameter. Then I have beta equal to 500. Gain is equal to 1 because in numerator I have k multiplied by beta. If beta is 500, then it means that k is equal to 1. Now I have 3 more parameters to find. I need to know what is my cutoff frequencies and what is my quality factor. So let's see how I can find them. The quality factor is easy because quality factor is equal to omega naught over beta. So if omega naught is 2000 and beta is 500, then it means it's equal to 4. So my Q is equal to 4. Now let's go to the cutoff frequencies. So I know that beta is equal to omega C2 minus omega C1. And I know that cutoff frequency is equal to, center frequency is equal to omega C2 multiplied by omega C1. So here, I know that the first equation is equal to 500 and the second one is equal to 2000. So I have two equations with two unknown. If I solve this equation, I'm going to have omega C1 equal to 1,765. And then by adding 500 to this number, I'm going to have my omega C2, which is going to be 2,265. So these are the last two parameters that I need to know about this particular filter. In next lecture, I'm going to focus on the transfer function of band reject filter, and we're going to see more examples.